In the beginning, there was a big bang. What do we mean by that? That means that the universe and everything in it started from a giant fireball of energy, and space has been expanding out from that fireball continuously ever since then for almost 14 billion years. Everything that we know about was created in that Big Bang. If we take a freeze frame of that Big Bang, though, we'll notice that something that you didn't see was also created then. Dark matter particles were created shortly after the Big Bang. So we say dark matter particles. What do we mean by that? Dark matter is some form of matter that doesn't emit light, doesn't reflect light, doesn't absorb light, doesn't do anything with light. So we take our light and our dark matter and our observer and we turn on the light. Nothing happens. The light goes straight through. It's as if the dark matter wasn't there at all. Normal matter doesn't act like that. Everything we know about might appear dark to our eyes, but that's because you have your light source and your normal matter and your observer turn on the light, and it either gets absorbed or reflected by the normal matter, but it is affected by it, whereas the dark matter doesn't have any effect on light or vice versa. So in that sense, a better name for dark matter might have been invisible matter, but then we couldn't call this dark matter day, could we? Why do we believe this dark matter exists? The reason is because wherever we look in the universe with telescopes, we see overwhelming evidence that there's something that, although we can't see it by light, we can see it by gravity. So there's this dark matter out there. We don't see it, but we have normal matter, and normal matter is gravitationally attracted to it. So something is out there and is affecting the motions of normal matter. Or is it possible that we don't understand gravity at all? Maybe the gravity that was predicted by Newton and Einstein, with the apple falling on Newton's head, isn't quite the same as the gravity we see way out in the universe. That's a possible scientific hypothesis, but it doesn't seem to work. All our theories of gravity have withstood every test up to now, and nobody has figured out a way to modify them to explain these observations that I just mentioned when we look out into the universe. So moving on to Act 2, let there be light and dark.
So Dan just showed you this picture showing the earliest moments of the universe and its subsequent expansion and evolution. And I want to talk now about a period of time about 300,000 years after the beginning, or about a little over 13 billion years ago, when the first atoms formed, a period called recombination, which is really the earliest that we can see directly with light today back in time. And this period of time, observations of this period of time, provide some of the strongest evidence, not only for dark matter, but of the fact that dark matter is of a fundamentally different nature than the normal matter. So what was the universe like at this early time? Well, it was kind of a soup of hot soup, let's say, of free protons, electrons, and photons that were buzzing around, bouncing off of, scattering off of these electrons and protons, something we call plasma. And as the universe expanded, kind of like a hot air balloon expanding, and time went on, it slowly started to cool. And eventually it cooled enough such that these protons and electrons lost enough energy that they could recombine into neutral hydrogen. Remember that a hydrogen atom is just one proton and one electron that are bound together. And neutral hydrogen, unlike this plasma at the hotter earlier times, is transparent to light. So all of this light that was scattering around suddenly was able to freely stream. That's what's shown or indicated by these yellow lines, freely stream, basically without ever interacting again throughout the entire history, remaining history of the universe. And we can go out and actually try to measure this light, and it provides a snapshot, a relatively pristine snapshot of what the universe looked like at this very, very early time, like 13 billion years ago. If this is a little bit difficult to grasp, an analogy that might help make a little more sense, although it's not a perfect analogy, so bear that in mind, is fog, a foggy day. So when on a foggy day, there are many water droplets in the atmosphere, and those water droplets scatter light. Light scatters off of them. And so it's difficult for you to see buildings such as these towers of the bridge in London in the background. But that water can condense, and when it does so, it falls as rain, and there are many fewer droplets in the atmosphere for water to scatter off of, and you can see much more clearly buildings in the background. That's a little bit like what's going on at recombination. In the before recombination, it's like the fog. After, it's like the rain. So you can go out and try to measure this light. It should be coming from all directions on the sky relatively uniformly. And it's what we call the cosmic microwave background. So that's what these two gentlemen here did with this funny looking antenna, or really it's kind of telescope. They had a very, very sensitive receiver, like a radio receiver, put it in the antenna and observed this very faint afterglow, essentially, from the Big Bang in all directions. This was the first evidence actually for the Big Bang model, that there was a period of time long ago when the universe was much hotter and much denser. Today, we still make these observations, much better versions of them, but using much more sophisticated techniques and technology. So just a couple of nice pictures of these experiments. On the left, there's a picture of the Planck satellite, which has many ultra cold detectors and was launched deep into space, far away from the heat from the Earth. And then on the right is a telescope that we actually built a camera for recently at Fermilab, called the South Pole Telescope. And there are many experiments like this located at high, dry, and remote places like the South Pole or Atacama Desert in Chile. So, and what these experiments measure is this really remarkable, beautiful picture like this. This is the all sky map of what the cosmic microwave background looks like in all directions on the sky. The red points and blue points are showing the fluctuations in temperature, or the brightness, essentially, in a way, of the light. And this may look like kind of a random pattern, but the statistics of this pattern, basically how big and how red or blue the dots look, are intimately related to what types of matter are in the universe, and provide us with really strong evidence for the existence of dark matter. And the reason why it does this is a little technical, but basically it's because these fluctuations that you see are the result of sound waves propagating in the early universe. So in the early universe, much like a wind instrument that has there's a fundamental mode, a lowest frequency, and then overtones or harmonics that are at somewhat higher frequencies, integer, the series of higher frequencies. And what you can do, the type of matter that these sound waves are propagating in results in slightly different types of waves, different wavelengths or amplitudes. And you can use measurements of these waves then to infer something about the types of matter that are producing the waves. So an example of this, a cartoon example of this, is imagine two different media for wave propagation. Depending on the nature of the medium, you end up with differences in the wave propagation. When you drop a pebble, let's say, into the pond, you get different types of waves. What we're seeing in the early universe is the result of many different pebbles that gives rise to this somewhat random pattern of fluctuations. But the statistics of that allow us to infer something about the medium, allow us to infer there's a certain amount of dark matter or a certain amount of normal matter, because it would give rise to a characteristically different pattern in this somewhat random looking cosmic microwave background map that we see here. And just to say that in a little more detail, part of the reason for that is because the dark matter doesn't interact with photons, as Dan said. So it tends to clump together, but it doesn't feel the force that the photons feel, unlike the normal matter. And so you end up with these pressure waves, essentially, that are different depending on the ratio of normal to dark matter. And that gives rise to a different distribution in the temperature of the light that we see from the early universe. And detailed measurements of that light and the sort of inference of measurements that we make from the cosmic microwave background have led us to this really remarkable conclusion that something like 70% of the total matter and energy budget in the universe is actually in the form of what we call dark energy. 25, a little over 25, is in the form of dark matter, and only about 5% or so is in the form of normal matter. And what these observations furthermore tell us is that the dark matter is fundamentally different than the normal matter because it doesn't interact with light in the same way as normal matter. So this is the mystery that we're all trying to solve, is what is this dark matter, which seems so fundamentally different from the ordinary matter and is the majority of the matter that we have in the universe.
Moving along in our timeline, Act 3, darkness rules.
Yeah, so picking up on the story that where Adam left us, we have these primordial fluctuations in the density of the universe. And because gravity is always attractive, those overdense regions end up getting more and more dense with time. And so the movie that's showing now is a computer simulation of what would happen if you start with the early fluctuations in the density of matter in the universe that we see imprinted on the cosmic microwave background, and allow those fluctuations to evolve over cosmic history. And what we're actually seeing here is what the structure of the universe would look like if we could actually see with dark matter eyes, or see the dark matter itself. So brighter regions in this simulation correspond to more dark matter. And what we see is that as the universe evolves, the universe as a whole is expanding, but the gravity is clumping and clustering the dark matter together. And so as time goes on, the dark matter gets more and more concentrated, more and more clumpy. And in fact, in the center of what we call these dark matter clouds, which we call dark matter halos, we end up seeing the visible galaxies form. And so on this scale, we're seeing a lot of dark matter clumping and clustering. And in the center, the brightest point, which is the highest density of dark matter, would live a galaxy somewhat like our own. And our own galaxy is relatively small on this scale. You can see it with this little inset picture at the bottom of your screen. And so as we run forward in time, we see this clumping and clustering of dark matter. Our simulations are predicting that we would see this clustered filamentary structure, sort of like soap bubbles, the edges of soap bubbles clustering together in dark matter space. And this prediction has been borne out by some of our largest telescopes, where we can go out and not measure the distribution of dark matter directly, but measure the distribution of the galaxies that live in the centers of these dark matter clumps. And we see that the two distributions look very much alike. And so this clustering and clumping of dark matter is occurring both on large scales that are larger than our galaxy, but also on scales that are much smaller than our galaxy. So if dark matter is slowly moving in the beginning of the universe, it can clump into very small clusters of dark matter, which would actually host small galaxies. And so our picture, again, if we could see the universe in dark matter, we would see this is a simulation in the background here as well, where bright regions indicate higher dark matter density. We would be able to see these clumps around our Milky Way galaxy. However, we can't see in dark matter, we see in invisible light. And so we can only see the galaxies that reside within these clumps of dark matter. And so we know about these largest galaxies, the Large Magellanic Cloud, but we can hypothesize that if our understanding of dark matter is correct, we should also see very small galaxies living in very small clumps of dark matter. So how do we find a really small galaxy? Well, the first thing that we would do is we'd jump on an airplane and fly down to Chile, because that's where some of our best and largest telescopes are. Once you get down to an oceanside town called La Serena, you would jump in a pickup truck and drive out into the foothills of the Andes, where we have these observatories that are roughly 2,000 meters above sea level, where it's very high and dry. So you don't have much atmosphere to look through and you don't have much cloud cover. You can build these really impressive telescopes to look for very faint objects in our universe. So this is what the top of one of those mountains looks like. This is Cerro Tololo Inter-American Observatory in Chile. And inside this big silver dome, we have a 4-meter large telescope called the Blanco telescope that looks like this. And on the front end of this telescope is a huge digital camera that's almost the size of a small car that's sort of held 15 meters above the mirror of this telescope. And it's a huge digital camera, much, much larger than the cameras you have in your cell phone. And for scale, you can see what the lowly cosmologist looks like standing next to this telescope here. And so with these really powerful instruments, we can go out and look for the small galaxies that we expect to live in these small clumps of dark matter around our galaxy. And this is what one of those galaxies looks like. And it's not Zoom that's playing tricks on you. This is actually an extremely faint galaxy that we actually detect by its individual stars. And so we can measure these very faint stars, and then we can perform velocity measurements on them that show us that they are all moving through space together. And so this is a gravitationally bound system. The stars in this galaxy are held together by the gravity of dark matter. And in fact, this galaxy would not exist. The stars would be unbound if there weren't the dark matter there to hold them together. And so this is observational proof that our Milky Way is surrounded by these small clumps of dark matter that host these extremely small galaxies. And this is actually something that allows us to test something about the fundamental nature of dark matter. Because if your dark matter particles were actually moving faster in the early universe, they weren't what we call cold or slow moving, they would have actually washed out these smallest structures and we wouldn't see any small galaxies around our Milky Way. So the fact that we see these small galaxies means that dark matter must have been slow moving in the early universe, and these warm dark matter or fast moving dark matter models are not allowed. Of course, we can't prove that we live in a completely cold dark matter universe, but this is a hypothesis that we continue to test at smaller and smaller scales. And so in our next act, we're going to talk a bit about what would happen if dark matter is not completely dark or invisible. So as you've heard, to the extent that our current observations are sensitive, we have not seen any indication that dark matter interacts with normal matter or with light. But our telescopes and observations get more and more sensitive every year. And so it could be that dark matter does interact just at a weak enough level, a faint enough level that we haven't been able to see it in the past. And if that's the case, we might expect that the brightest signals from some kind of dark matter interaction would occur in the regions of space where the dark matter density is the highest. These are the most concentrated regions of dark matter. And so these are the places that we want to direct our telescopes and observations to try and see any possible signature of not completely dark matter. So what we would see when looking, or we hypothesize we could see when looking at one of these clumps of dark matter, is some faint glow in particles of normal matter that could be produced when two dark matter particles come together and annihilate. Or if dark matter is not completely stable, it could decay and produce normal matter particles. These could be neutral particles like photons of light, or neutrinos, which are a very weakly interacting particle, in which case those particles would travel straight to our detectors on Earth, and we could point directly back to the clumps of dark matter in our universe. On the other hand, these interactions that dark matter may have could produce charged particles, and charged particles get caught up in electric and magnetic fields in the universe and get all scrambled up. And so we may see the signature of these charged particles, but we would have a much harder time pointing them back to where they originated. So how do we make these detections of energetic particles from space? Well, we have a few different detector technologies. So one is to launch satellites into space. And in space, you can have one of these energetic particles potentially coming from a dark matter interaction and annihilation or decay, come into your detector, interact in your detector, and produce photons or electrons, either by scattering or annihilation of its own. And you can then detect those those normal matter particles in your detector in observatories like the Fermi Large Area Telescope that's in orbit around Earth. On the ground, you can also use our atmosphere itself to be the conversion material. So a photon or a proton or a gamma ray, a highly energetic particle, can enter our atmosphere, interact in our atmosphere, and lead to a shower of energetic particles that can be detected by telescopes that we actually have on the ground. And one example of a detector array like that is the HESS telescope, which is in Africa. Finally, for even less interactive particles like neutrinos, they can actually pass through our atmosphere without interacting at all. They can pass down into oceans or the ice sheets in the Antarctic, where they may then interact with the molecules of water and shower to produce, again, energetic particles that can be detected by very sensitive detectors that we bury either in strings in the ice or underwater on the ocean, attached to the ocean floor. And one example of an instrument like this is the ice cube array that is in Antarctica. And so, of course, it's challenging. We can detect these particles, and we do detect these normal matter particles showering down on Earth all the time. But it is challenging, very hard to understand whether they were produced by normal astrophysical processes, such as black holes shooting out energetic jets of particles, or rapidly rotating neutron stars, which can also give you jets of energetic particles, or whether they were actually produced by some dark matter process. And so the way we try to test this is by looking out, observing our universe, looking at regions where we expect high densities of dark matter, like the center of our galaxy. So this is a map of our entire sky, with our Milky Way being this bright band cutting across the middle of our picture, and the center of our Milky Way being located in the center of the picture. So we can go and look at the center of our Milky Way, which is located in the center of this very massive dark matter halo, and we can see if we detect any excess emission coming from that region of the sky. And we do see some extra emission that we can't explain with astrophysical processes, at least to the level that we understand them today. However, this makes a prediction that when we look out at other places where we know there's a high density of dark matter, such as these very small galaxies that we find located around our Milky Way, we would, if a signature from the center of the galaxy is coming from a dark matter interaction, we would also expect to see some dark matter interaction signal coming from these small galaxies. And right now, to the sensitivity of our current telescopes, we don't see any signature there. And so this is sort of a conundrum. It's sort of one of these unanswered questions that we have in science today is, what is making up this mysterious emission coming from the center of our galaxy? And why aren't we seeing any corresponding emission in these small galaxies around the Milky Way?
Moving on to Act 5, scattering the dark.
We have seen in the previous acts that dark matter is everywhere in the universe. And so we can see our solar system that is moving through the Milky Way halo. And so we can imagine that our Earth, ourselves, and everything is encountering like a wind of dark matter. It's similar to the effect of when we are traveling in a car and we are seeing a kind of relative wind hitting our car. Or if we put, for example, a hand out of the windshield, the window. So we have seen that we are saying that essentially for each second, about 20 million of dark matter particles are crossing our hands continuously. But it's such a small interaction that we are not able to feel anything. But at this point, we can imagine to substitute our hand with a dark matter detector and try to capture one of these faint interactions. these interactions, we can think about this kind of interaction like the billiard, playing like billiard. We can imagine that the dark matter particle is the white ball, and our detector is the remaining set of balls. And so when the white balls hit the other balls, it deposits some energy, and then it scatters away and goes away. And so we are able to measure the energy released in the detector. We expect extremely rare signals. So we expect a few events per detector per year. And to give an idea, to compare these, the quantity of the signal to events that could be close to our detector. For example, if we put our detector in the same room in which we are, one person of 70 kilograms would generate 4,000 events per second in the detector. Or if we put a banana, it would generate in the detector 13 events per second, something like this. Even particles from the sky, the cosmic ray radiation would create events in this detector. For example, we have that per each second, we have at least 1 million events passing through our hands. And so we can imagine to give an idea of the number of these events, to look at them and convert them to light and audio frequencies. And so, for example, this one showing some radioactivity and how it's affected by the detector. The second one, the second video, is showing the radiation from the sky. And so cosmic ray and muons, as we were saying before. And the last one is showing what could be the background after shielding the detector. And so in order to detect dark matter, this scattering dark matter, we need to protect from radioactivity our detectors. And so first of all, we go underground, and in order to shield from the cosmic ray radiation. In the picture, we have a laboratory as SNOLAB that is as an above ground laboratory and the underground laboratory, which is 2 kilometers underground, which is equivalent of in height to 6 Eiffel Towers. It's a 6 Eiffel Tower deep in the ground. Another way we are playing with Lego. Well, not exactly not with real Lego, but we are building really big shield with tiny bricks of lead in order to protect for ambient radioactivity, to protect our detectors from ambient radioactivity. And then we care really a lot about cleanliness and radioactivity control. And so we work in very clean suits.
Okay. So in the previous talk, we heard that the dark matter particle is everywhere in the universe. And I'm going to talk about how we can build experiments in our lab on the Earth. And if a dark matter particle is crossing through this space, then we can probably detect it. We have also heard from the previous acts that although dark matter consists of about 25% of the mass in the universe, but we still don't know the mass or the frequency of this dark matter particle. So if we build a radio type detector in the lab, and we can listen to the dark matter signal if we dial the correct frequency. However, since this dark matter particle interacts very, very weakly with our normal matter, it's difficult to get a very good signal, and we have to turn down the background noise on this radio. So in order to do that, we cool down our radio to a temperature which is almost 100 times colder than the outer space, and see if we can spot the signal. Here is an experiment that is going on at Fermilab. On the left-hand side, I'm showing an image of the actual experiment And on the right-hand side, I am showing how the inside of such a fridge looks like. And this is a very special type of equipment where we use a mixture of helium isotopes to cool down the temperature of this entire instrument to, as I mentioned earlier, 100 times lower than the temperature of the outer space. And on the bottoms, you can see a microwave cavity or a fancy radio, which is hanging from the fridge, where we cool down the temperature to get rid of any thermal motions inside this cavity. And we can use very novel detectors that we have developed here at Fermilab to count the number of photons which are deposited by the dark matter particle. And these counters help us lower the background noise to a very low level such that we can start seeing the dark matter signal. And one way to think about this counter is we just make artificial atoms. And we know that atoms absorb light, and based on the number of photons that the atoms absorb, we can infer how many photons were deposited by the dark matter particle, and so on.
Act 6, cooking up dark matter.
Okay, so moving up to our next act, we've explored that dark matter the hypothesis that dark matter maybe come to us as a wind of dark matter. But if it doesn't come to us, we can explore something opposite where we come to dark matter, where we originate or produce dark matter. This has an assumption that dark matter may behave as everything else in our universe fundamentally in the form of particles. So now we start thinking about particles, and we start thinking also about how we usually produce particles here at Earth. And one particular setup that we as particle physicists like are particle accelerators. So particle accelerators are both useful to produce a ton of particles and also produce particles with very high energies. We can consider two types of accelerators that I'm going to talk about here. One is a collider setup, where you have two beams colliding against each other, two beams of particles. And in the point of the collision, you build a detector that tries to identify everything that comes out of that collision. The other setup is called a fixed target setup. This only needs one beam of particles that goes in one direction, hits a target that is usually made of some sort of nuclei, and then you place a detector upstream of that target or downstream that target, and again try to detect the products of that collision. There are two examples that I want to give here of actual accelerators that live here on Earth. The first one is called the Large Hadron Collider. Many refer to it as the LHC. This is a big collider that is in the border between Switzerland and France. There's Geneva, the city. It's also underground, and it collides beams of protons at very high energies, that they achieve very large velocities. There are 4 collision points, and around each of these collision points, there are again built some detectors. If you're curious of what a particle collision looks like, we have an actual image here. At the end, what you end up seeing after these two beams of protons collide is really a bunch of particles that come out of that very high energy collision. These particles that come out of that collision can be actually tracked. This is why you see each of these lines that come out of the center point. And depending on either the curvature of those lines or how far those lines reach, we can tell what kind of particles have been produced in that collision. Finally, there's also another experiment, which I can also give you an example of a fixed target setup, where you actually have an electron beam that is inciting in top of one nuclei target. It's a very thin target. This is called the Light Dark Matter Experiment, LDMX. And after that target, you actually place again some material, either on some detectors that can trace what comes out of that electron target collision. You would still expect to see the electron that was incident, but also maybe something else that gets produced with the electron. I want to emphasize, though, that one thing about these experiments is that also the scale is usually quite different. there are two pictures, one of the detectors in the Large Hadron Collider in the left, and one of the magnets that is used in this is the electron fixed target experiment on the right. And there are two people kind of standing next to each of these images. And the scale really is very different, especially for these very large very powerful accelerators or colliders. You usually end up building very large detectors, whereas for these fixed target setups, things are a little different and you need a much smaller scale. So now actually coming back to dark matter, how can we actually produce dark matter with these experiments? There are two hypotheses that we can use. Both of them use the hypothesis that that when particles collide, they may achieve either very large intensity, so there's lots of particles or very large energies, and they can produce dark matter in these collisions. So really energetic beams, which are here just simulated by these two needles that are colliding with each other, can produce very heavy dark matter particles, but it's quite hard to collide them exactly next to each other. That's why we need a collider setup that can accelerate them to very high energies. If we don't have the capability of accelerating them to very high energies, we can use these fixed target experiments, which can actually use very intense beams, so lots of particles, lots of needles going into this target and producing dark matter. So actually, what do these experiments see? In contrary of any of the experiments that we saw in the last act, all of these detectors are not built to detect dark matter. They're actually built to detect ordinary matter particles like photons, muons, electrons, hadrons, quarks. And this means that if dark matter is made in these collisions, we won't be able to detect it with using these detectors. So what is our approach? We can usually use two questions that we try to answer to see if dark matter was produced in these collisions. The first one is, was energy and mass conserved in these collisions? We know the energy of the initial particles. That energy and mass should be conserved by looking at the outgoing particles. If there's an imbalance, we know that there's something missing, and that points us to the existence of dark matter. The second is also related to a hypothesis where dark matter can actually interact with ordinary matter particles, or some other kind of particles that can produce normal particles, that can produce muons, can produce electrons. And therefore, if we detect these muons and electrons and see if something fishy is going on with them, that can point us again back to the hypothesis of dark matter being produced.
Finally, Act 7, how will it all end? My exceptional young colleagues have convinced you, I hope, that the universe is made of a little bit of ordinary matter, a lot of dark matter, and some mysterious thing called dark energy. We don't know for sure what the balance is between those and how that evolves with time. What if dark energy dominates? What if it's this huge, ugly cloud in the room? What will happen to the universe? That scenario is called the Big Rip, where dark energy wins and vanquishes dark matter and ordinary matter. And to visualize that with a simulation, what happens is that not only do the galaxies spread apart from each other, but ultimately they get ripped apart, the stars get ripped apart, all ordinary matter dissolves. Not a pretty picture, not a scenario we'd like to see happen. But don't worry too much about it. It's billions and billions of years in the future. But that doesn't have to be the way it ends. There's another scenario where dark energy isn't quite this huge, ugly cloud. It's a little bit less dominant over dark matter and normal matter. If that's the case, then the universe is still expanding. The galaxies are still moving away from each other. From our vantage point, we see fewer and fewer of them. So the universe looks darker and darker and becomes colder and colder. But normal matter does not get disrupted. So in the end, we're alone, but we're not torn apart. Still a better scenario than the Big Rip. Finally, what happens if dark matter wins? Dark energy isn't the gorilla in the room. Then the universe collapses back on itself and perhaps restarts another universe with another Big Bang. And we play out the scenario all over, although we don't. Our people who inherit the new universe will see how it turns out in their universe. That's our play. We would like to, if you would like to learn more about dark matter, there are plenty of resources on darkmatterday.com or these other websites here. We encourage you to look at those.